In today's lecture, we will address the topic of climate and specifically how climate changes through time. The lecture will address the larger overarching questions of where and what our place in space and time is, and how human civilization and our planet interact. At the end of the lectures, students will be able to distinguish between natural and anthropogenic causes of climate change, tell and analyze the predicted consequences of climate change, and identify problems of climate change that arise for our society. Climate change is the change in the statistical distribution of weather patterns when that change lasts for an extended period of time, and that may be on the order of decades all the way up to millions of years. And in this graphic here, where we have the average temperatures plotted against hotter and colder temperatures from 1880 to 2014, we can really highlight what climate change is portrayed as in society. Here in this, we're only looking on the order of decades, so we're really looking on the order of measurable and human timescales, where we started measuring weather, where we started recording weather patterns, and we find that, as indicated by this dark black curve here, thick black curve, that we really had an average. We were always around the average in terms of the temperatures in the early 1900s and late 1800s, but then around the mid 1950s, we started deviating from average only in one direction. We went hotter and hotter ever since. And at this point, we are approximately already 2 degrees Fahrenheit hotter than the average from 1880 to 2014. But as you all know, climate, we have multiple factors that operate on much longer timescales, especially astronomical factors and terrestrial factors. So natural factors that are either extraterrestrial, coming from our solar system, or from within our planet. And as a third category here, we have anthropogenic factors that also play a role. Looking at those factors, what were they? For the astronomical factors, we learned about solar radiation or solar forcing, how much energy arrives at our planet. Albedo means the brightness of our planet and how much energy gets reflected off of our planet. And some astronomical factors involving our Earth's orbit. This includes the actual tilt, the Earth's precession, and the eccentricity. In addition, factors like the arrangement of continents, the topography of our land masses, what elevation we have, and especially volcanism govern climate. On the other hand, anthropogenic factors include aerosols. Remember, these are little particles, solid or liquid particles that are contained in the air. How we use our lands, and also industrial greenhouse gas emission. Before we go into the actual outcomes of what climate change does to our planet, how do geologists study climate change is the question. For that, we use isotopes. Remember, we already talked about radiogenic isotopes for detection of absolute ages of rocks, but we can also use isotopes for studying climate change. For that, we use oxygen as an isotopic system. And oxygen has two predominant isotopes that are stable. We call those oxygen-16 and oxygen-18. Oxygen-16 has 8 protons and 8 neutrons. That makes an atomic mass of approximately 16 units. Whereas oxygen-18 has 8 protons and 10 neutrons, making an approximate atomic mass of 18 units. So we have a lighter oxygen and a heavier oxygen isotope around to study as a stable isotope system. As part of the Earth and as part of the Earth system, oxygen occurs very abundantly throughout our crust and at the surface of our Earth. Remember, oxygen is the most abundant chemical element in our crust, but also is contained in water as H2O, which water is in the ocean, is trapped in the ice caps, and can be trapped in clouds. And so oxygen moves around quite a bit on our planet. In the ocean, also, water may be precipitated out of solution and form limestone. And limestones are carbonates and predominantly contain calcium carbonate as a mineral. And so we can study also calcium carbonate to how it contains multiple ratios of heavy to light oxygen isotopes. So in the atmosphere, we can store a lot of energy if we are a little warmer. And so if we are having a warm atmosphere, we may evaporate lots of water from the ocean, and that includes the lighter version and the heavier version of the oxygen isotope that is trapped inside the water. This water then may migrate over land and towards the pole, and when it rains, the heavier water is preferred to rain out of the cloud, whereas the lighter water is preferred to stay within the cloud. So usually inside clouds, the lighter oxygen isotope, oxygen-16, is enriched, whereas the heavier isotope, oxygen-18, is depleted. Then when we are at the pole and the clouds snow out the rest of the water over the ice caps to make glaciers and ice sheets, we actually have more oxygen-16 inside the snow, and so we enrich oxygen-16 in the ice and deplete oxygen-18 in the ice. During a warmer temperature then, we actually take more oxygen-18 evaporate more oxygen-18 out of the water and move towards the pole, and the likelihood that oxygen-18 makes it to the pole is greater in warmer climates. That means for warmer climates that less oxygen-18 is contained within within the oceans. And so less oxygen-18 may be trapped within carbon in the calcium carbonate. During colder climates, on the other hand, more oxygen-18 may remain in the ocean and be trapped inside fossils and inside the calcium carbonate, and less oxygen-18 may migrate inside the clouds towards the pole and snow out as ice onto the ice caps and glaciers. And so to recap, a higher abundance of oxygen-18 in carbonates is indicative of colder water and colder water temperatures, since the lighter isotopes are all stored in glacial ice. And geologists have actually studied that. From fossils, we can study the calcium carbonate inside fossils, and we can take ice cores, especially in more recent times, where we have lots of ice available in the form of the ice sheet on Antarctica and Greenland. So in this graphic, this shows the oxygen-18 abundance on the y-axis as a function of time on the x-axis, from most recent times closer to the origin to the most ancient times in terms of the Phanerozoic, the Cambrian, in farther away from the origin. Remember, the letters represent the individual periods of our Phanerozoic, the Neogene and Paleogene, then the Cretaceous, Jurassic, and Triassic, and the Permian, Carboniferous, Devonian, Silurian, Ordovician, and Cambrian. And based on the oxygen-18 amount entrapped inside fossils, we can actually study how cold or how hot it was on our planet. Currently, we are in a colder period of our Earth's history, and when we look back into the Cretaceous, we actually can see that we were in a hotter part of our Earth's history. Then throughout the Mesozoic here, Jurassic and Triassic, we were not too cold, not too warm, but we were fairly warm then back at the end of the Paleozoic in terms of the Permian and a little bit of the Carboniferous, but during most of the Carboniferous we were in much colder temperatures. Then temperatures increased again during the Devonian and fell during the Silurian and Ordovician to the coldest temperatures that we can actually detect to have occurred throughout the Phanerozoic. What this graphic shows you is that, based on geologic time, climate changed throughout all the different periods of our Phanerozoic, and climate change is nothing uncommon throughout our geologic history. When we look at that and compare it to the Milankovitch cycles, we actually can see that there is a fairly good correlation between our astronomical factors and the fossil record and the record of oxygen isotopes stored in our polar caps. Remember, we have the Milankovitch cycles, which include the tilt of our axis of the Earth, which we term obliquity, and the shape of our orbit around the Sun, which is eccentricity. Sometimes we have fairly elliptical orbits, and other times we have fairly circular orbits. We also have two factors called precession, where we slowly migrate not only the eccentricity of our orbit, but also the tilt of our Earth. For the astronomical factors, our solar forcing plays a role as well, so how much energy is actually arriving at the surface of our Earth. And then we can actually measure the changes in oxygen ratios for, in brown here, calcium carbonate in, for example, benthic forms, so this is a fossil containing calcium carbonate, as well as the oxygen 18 ratio to what is contained within ice in the Antarctic ice sheet for at least the last 400,000 years. And the takeaway point is here that on the order of tens to hundreds of thousands of years in the past, climate has changed, as we can see, basically governed by changes in the astronomical factors on orders of tens to hundreds of thousands of years. And these changes are actually represented in the oxygen isotope ratios in not only fossils but also in ice.